Good morning, good afternoon, or good evening. Thank you for joining us for episode 32 in the Gleeble webinar series. My name is Dan Quigley, and I'm joined today from a very snowy and cold upstate New York, but we're glad that you're here. Today is December 17th, 2020, and we have almost finished one of the strangest and maybe most challenging years in recent history. I want to take a minute to thank the Gleeble community for participating in this webinar series. Today's session is our 32nd webinar this year. And we launched this webinar series back in April as the world shut down and conferences were being canceled. And to be honest, the webinars have been more popular and even better received than we expected. In fact, we have over 200 people registered for today's presentation. We are very fortunate to have some of the smartest, most creative, and accomplished users in the world. So I want to take a moment to thank all of our past presenters that have helped make this such a successful series. We've seen many presentations over the past year that prove how valuable the community's research is. The work that you're all doing is so important. You're changing and improving the world. And on behalf of our whole team here at DSI, we're grateful for the work that you do, and it's our honor to provide the equipment, service, and expertise to help you along your way. This will be the last webinar of 2020. We will be taking a break for a few weeks around the holidays, but we will be back in early 2021. Please look for an email from me or our team with scheduling updates, probably in mid-January. Today's presentation is titled Gleeble Supported Steel Weldability Research at BaoSteel and will be presented by Dr. Zhaoxia Chu. Dr. Chu is a chief researcher focusing on welding at the Central Research Institute of BaoSteel and is responsible for the development of high-end welding consumables, steel weldability evaluation, and advanced welding technology development. Research of her work on a series of key welding technologies have improved welding quality and promoted process optimization and technical improvements for BaoSteel customers. The presentation will include 4 topics, including a brief introduction of steels and welding consumables, an introduction of weldability, a discussion of Gleeble welding research including specific cases and examples, and finally an introduction to the relationship between physical simulation and numerical simulation. As always, we encourage the audience to ask questions during the presentation using the chat window. Dr. Chu has pre-recorded her presentation, and I'll play that video in a moment. But because it's pre-recorded, she will be available here to answer questions during the presentation via chat. So we won't do our normal Q&A at the end of the presentation. We'll do it during, through which you have to type in the questions. And you get hopefully typed responses either from Dr. Chu or members of the team here at DSI. As always, video of this presentation will also be available online. I'll get that posted soon. Certificates will be emailed if you're listening to this live. And you'll be able to find a link to this video as well as videos of past webinars by going to our website at gleeble.com and then clicking on the resources link in the top navigation bar. Once you're there, click on webinars, and there you can view past webinars, sign up for future webinars. I do want to thank Dr. Chu for preparing this presentation and for joining us here today to answer our questions. So I'll go ahead and I'll play this video. It will run for about 52 minutes, and then I do encourage you to ask questions during. Thank you. Please enjoy.
Thanks, Dan. Hello, everyone. I'm very honored to be here and meet you all on this platform. Today, the topic is Gleeble supported steel weldability research at BaoSteel. Being a welding engineer working in a steelmaker company, BaoSteel, I try my best to build a bridge of communication between BaoSteel and steel customer through our welding technology support. BaoSteel, our headquarters located in Shanghai, China. In order to support our customer well, I got an international welding engineer in the year of 2002, and got a certified welding inspector in the year of 2012. There are about 4 stages from steel development to mass use by our end customers, like R&D development stage, industry trial production stage, market development stage, and massive application stage. Each stage will focus on different welding technicals. For example, in R&D stage, steel weldability evaluation will be paid more attention, which is just our topic today. In the industry trial production stage, will focus on the lower and upper point of the chemical composition on weldability. On the marketing development stage, we will focus on the industry field and their standards. We will do some research about their products life, service life. On the final manufacturing stage, the massive application, that is our under customers will focus on the making welding specific welding processes specification and how to evaluate the qualified welding operator personnel. There will be 4 parts totally in these slides. Part A is a brief introduction of steels and welding consumables. Part B is introduction of weldability. And Part C is the discussion of Gleeble welding research. Part D is the relationship between physical simulation and numerical simulation. Let's get started. Part A is a brief introduction of steels and welding consumables. This is the production process flow chart of hot rolled sheet. Beginning from iron ore and coal and ending in our commercial steel products. Next is our welding consumables. This is the electrode of SMAW. The electrode length is about from 250 millimeters to 400 millimeters in length, which are steel rods covered by flux. This mark wire is packaged in reels. A standard weight is usually 15 to 20 kilograms. The oven diameter for it is 1.2 or 1.0 millimeters. Mostly, the mark welding wire is solid. For submerged arc welding, the welding consumables are made of welding wires and the matched flux. Of course, there were several kinds of flux, and there were a lot of kinds of welding wire. The biggest difference from mark wire is their diameter is much larger. Usually, it's 4.0 or 5.0 millimeters. For TIG and PAW welding, the welding wire is as a filler metal, not as an electrode. Usually, it is about 1 meter in length, and the diameter usually is 2.4 millimeters. This picture is our welding wire rod produced by BaoSteel. The diameter usually is 5.5 or 6.5 millimeter. After pressing and joining, it becomes the welding consumables as we just introduced above. This is the production process flow chart of a welding wire rod. It is also the process from iron ore and coal to our commercial steel rod product, very similar to steel production process. Next, we'll introduce the matching rules for welding consumables and steels. The most used rule is the equal strength and equal toughness. It is suitable for most situations, especially for structural steels. The second rule is the special function property priority. It is suitable for some steels having a special function properties, such as the weathering steel, wear-resistant steel, heat-resistant steel, and HCT. Welded joints can be formed when steels and welding consumables are ready. The joint includes 3 parts roughly, named base mantle, welding mantle, and the heat-affected zone. Heat-affected zone can be divided into several zones, as shown in this picture. For example, the part C, D, and E, it's altogether is called the heat-affected zone. Of course, each part of zone has different mechanical properties. So, in order to meet the design requirement of the structure, we have to figure out which zone has the weakest performance. What suggestions can be given to improve the properties of the entire joint? This is part of A. Next, let's begin part B. Part B is an introduction of the weldability. There are 2 aspects about this concept. One is the sensitivity to weld crack. The other is the range of welding process parameters. For the sensitivity of a weld crack, we hope it is as low as possible. For the range of welding process parameters, we hope it is as large as possible. That is to say, we hope it is large enough, because in that way, welding operators of all levels can do a good job. In that way, our steels can be used in much wider application fields. So, the welded joint will have a good quality, whatever who make it, whatever what situations it is. In terms of weld crack sensitivity, taking cold cracking as an example, it has 3 key facts, such as the first is the hydrogen level, the second is the hardening tendency, and the third is the restraint condition. We also call it the structural constraint. Among three factors, the hardening tendency reflects the effect of the chemical composition of a steel on its weldability. As for the range of welding parameters, it is depend not only the SHCCT curve, but also the range of matched welding heat input. That is also called the adaptability of different heat input. We hope the heat input as wide as enough. The part C is the discussion of Gleeble welding research. This is also the main body of today's topic. Weldability research can be used to direct the composition design of steels and welding consumables. For example, the hot crack tendency can be evaluated by the value of non-ductivity temperature and brittle temperature range, which is obtained from the high temperature tensile testing. The cold crack tendency can be obtained from the test of simulated HAZ hardness. SHCCT curve is the base of making a welding process specification. The welding process specification we also call a WPS. It's very important for our customer to use our products. Next is a list of some specific Gleeble application scenarios. The first is the microstructure of the simulated HAZ. We can simulate the microstructure our interested location in the heat affected zone. The simulation temperature program takes different welding thermocycles with different peak temperature and different cooling rate. We also characterized with T85. In this tester, the samples are usually round. These are the simulated microstructure of coarse-grained HAZ. From this picture, you can know the peak temperature is 1,350 centigrade, and the cooling rate T8 cooling rate we described by the T85. It is the time from the 800 to cool to 500 centigrade. The T85 is different. It's 20 seconds, 50 seconds. And we also compare the peak temperature is 800 centigrade. The microstructure is different, and also sometimes the mechanical properties is different. The simulated microstructure are in good agreement with actual joints in terms both of the type of microstructures and the grain size. This picture shows the comparison between the simulated and the actual weld joints. This shows that the Gleeble system is very reliable in physical simulation. Second, the impact toughness of simulated HEZ at the interested position can be obtained. In this test, the square sample is required. This is the examples we do. And the test is the different peak temperature and the different the cooling rate. Thirdly, SHCCT curves can be investigated and joined. The round bar samples are heated rapidly to 1350 centigrades and then cooled at different rates according to designed temperature progress. During the process, the thermal expansion in real time can be recorded so that the transformation points at different T85 can be obtained by determining the temperature of inflection point in a thermal expansion curve. Meanwhile, the max structures and hardness at different cooling rates are observed and measured. Finally, putting the three things together, the SHCCT curve of the material can be drawn like this. This is a SHCCT curve of an ultra high strength steel produced by BaoSteel. This is just an example. This is the SHCCT curves of a series of ultra high strength welding consumables. Actually, it's a series of mark welding wire with different mechanical properties. Fourthly, a welding process can be analyzed using Gleeble system. The welding thermal cycles of single run welding and multi-layer welding can be simulated by designing a series of parameters like the heating rate, the peak temperature, the cooling rate, then the microstructures hardness can be obtained. We can compare and analyze and then decide which welding process is good. This slide shows an example of a single run welding, which means that only one welding thermal cycle is applied to samples. We can see the tendency of hardening, softening, and embrittlement of steel's heat-affected zone. Hardening and softening tendency are mainly reflected by hardness tests, while embrittlement property is mainly reflected by the impact toughness test. This slide shows an example of multi-layer welding, which means multi-welding thermal cycles are required. Of course, it needs a well-designed temperature program if you want the better effect. Like single-run welding, the tendency of HAZ, hardening, softening, and embrittlement of multi-layer welding can be got. Fifthly, a process of a post-weld heat treatment process can be optimized. Which process is better become found according to properties and microstructures by simulating different post-weld heat treatment processes using Gleeble system. For example, we can design different simulate parameters. For example, the heating rate, coating temperature, the holding time, a cooling rate, just like that. For more accuracy, welding residual stresses can also be superimposed. Next, we'll introduce the sixth application scenarios. It can be used to measure the material's high temperature performance data. Some materials' high temperature data, such as the yield strength, tensile strength, and the reduction area at elevated temperature, can be obtained directly through the test. Of course, the experiment process is like that. The sample is heated to certain temperature, holding for some time, and then the samples are pulled to break, so we can get some direct results. Also, we can get some indirect results, like the nail strength temperature, the nail ductility temperature, the ductility recovery temperature, and the brittle temperature range, and the nail ductility range. Also, they have some some special name for the welding engineer. For example, the nail strength temperature we call NST. The nail ductility temperature we call NDT. The ductility recovery temperature we call the DRT. And the brittle temperature range we call the BTR. Nail ductility range we call the NDR. What does it mean? We'll introduce in the next. The NST can be used as a criterion for weld solidification cracking. What is the NST? That means the strength will be zero when the temperature is over the NST. That means that any small load applied will lead to crack. The hot crack, a crack formed at temperatures near a completion of solidification, including weld solidification cracking HAZ liquidation cracking and Weldability liquidation cracking. The NDT is also a good index for HAZ liquidation cracking. When the temperature is over NDT, samples will go brittle, completely losing their ductility. In this, I don't introduce the experiment process. The values of BTR and NDR can be further used as the criteria for both forms of the hot cracking, that is the solidification cracking and the liquidation cracking. The BTR is the temperature range near the solid phase line when the solid and liquid coexist. NDR, the temperature range near the weld in HAZ when the ductility is close to 0. So this data we often use in our company, in our research. Seventhly, it can be used to analyze the tendency of reheat cracking. For example, reheat cracking occurs when HAZ is reheated during post-weld heat treatment or in a high surface temperature. Applied welding thermocycle to samples first, doing tensile tests at different high temperature after holding for some time, recording the area reduction and yield strength corresponding to various high temperatures, and calculated the reheat cracking sensitive temperature range. Judge the reheat cracking tendency based on the temperature range. Through this, we can analyze the tendency of the steel's reheat cracking tendency. Last one, but not the least one, is to analyze the cold cracking tendency. Applying 3 factors together to the samples, namely hardening microstructures, a certain amount of hydrogen, and welding stresses, we can get some data about cold cracking sensitivity for various steels. Because the cold cracking is very important for us, so there are a lot of experiments we can evaluate. So the physical simulation is just one of them. Next, let's look at some specific application cases of Gleeble welding research at BaoSteel. Case 1 is the weldability research of an ultra-high strength steel produced by BaoSteel. For a new developed steel product, generally its SHCCT curve should be plotted as early as possible. The HCCT samples are round, as shown in the picture. there are two types of samples. The first one is is used when the cooling rate is very fast. Microstructures of simulated coarse-grained HAZ are shown in this slide. The thermal cycles are that the peak temperature is 1350 centigrade and the cooling time G85 is different. It's from the T85 is from 5 seconds to 300 seconds. So the microstructure is different. We can see the microstructure how to involve in different cooling time. This is the final SHCCT diagram of an ultra-high strength steel, including the hardness, microstructure, and transformation information. And it can be seen from this SHCCT curve that martensite will be found in a wide range of cooling rate, which means that the steel has a strong tendency of cold cracking. So cold cracking should be paid more attention in establishing their welding process specification. This picture shows the impactor of toughness of a simulated coarse-grained heat effect zone with different cooling rate at a low temperature of minus 20 centigrade. From this picture, it is known that the coarse-grained HAZ has the best property when the T85 is 14 seconds. Next up, we talk about the case 2. Case 2 is to measure high temperature strengths of steels. The actual temperature curve performed by Gleeble system is in good agreement with the design. The sample for high temperature tensile as shown in this picture. The stress strain curves can be recorded when the specimens are poured at a certain temperature, so we can get the yield strength of steel with different chemical composition design. So analyzing and comparing the result, the steel with some chemical composition that meets the requirements of high temperature strengths can then be selected. So it is very useful for us to select the steel's chemical composition. Case 3 is about reheat cracking research. Reheat cracking occurs when the welded joints are reheated within a certain temperature range, such as the post-weld heat treatment. The stress-relieved heat treatment is a common PWHT heat treatment. It's common for pressure vessel steels and heavy plates. Usually, a reheat cracking reheat crack starts in coarse-grained heat-affected zone and ends in the fine-grained HAZ. The test process is as following. The first step is to form a weld metal and its HAZ by carrying out TIG spot welding in the center of the sample. The second step is to apply a certain strain at a specific high temperature. The last step is to check cracks by metallographic inspection. Post-weld heat treatment process or the chemical composition design of some tensile steels then can be optimized according to the test results. This is the metallographic observation of the welding zone at the temperature of 780 centigrades with different strain. It's from 6%, 10% and 20% of the strain respectively. In the end, the active strain, for example, the strain of 20% causes the sample to break. So this is our this is all about part C. Next, let's introduce the part D. Part D is Part D is about the relationship between the physical simulation and the numerical simulation. Generally speaking, nowadays numerical simulation is becoming more and more in a fashion. Today I want to emphasize the physical simulation is the base of the numerical simulation. And if the numerical simulation based on physical simulation, then it will be more accurate, will be a better application. So let's look at an example in our company. Numerical simulation is very useful, and this is a H-beam made of hot-rolled high-strength steel. The H-beam is the main load-bearing member, so there will be more strict requirement for its size and deformation. The deformation is mainly caused by welding. The different level of welding deformation represents the different manufacturing level of the company. The welding process involves a coupling among temperature, microstructures, and the structure and the stress. So the deformation of weld structure contains the three factors. That is the mechanical, and the thermal, and the metallurgical factor. So the welding deformation of the structure also comes from these three sides. Just like the equation, the totally the welding deformation equals to the elastic and the plastic strain. They belong to the mechanical analysis, so we should be considerate. For the third part is the thermal strain. This is the thermal analysis. The thermal strain is caused by different welding processes. The last one is for metallurgical analysis. The metallurgical strain is caused by martensite transformation. It should be considered for high and ultra high strength steels. So the welded joints include three parts roughly. It is the weld mantle. It's mainly made of the welding consumables. And the base mantle, it is ultra high strength steel. And it's HAZ, the heat affected zone. It can also be divided into several parts. Their mechanical properties is very different. So in the material model of the numerical simulation, the three parts should be considered respectively if you want to have a good effect. In the material model, the physical parameters of three parts must be considered, such as the specific heat capacity, thermal conductivity coefficient, density, elastic modulus, Poisson's ratio, yield strength, and linear expansion coefficient. Gleeble system can be used to measure the SHCCT curve of the base mantle and of the welding consumables. If this data can be input to the material model of the numerical simulation, then the numerical simulation will be accurate. We also can get the yield strength of a series of high temperature obtained through the Gleeble system testing. Once these data are input to the material model, the result of the numerical model will be perfect. We try to do this. Considering phase transformation in the numerical simulation model for the ultra-high strength steel structure, the microstructure and proportional distribution in a welded joint section are shown in this figure. Also, the welding temperature field are also shown in this picture. Now let's talk about the result of the numerical simulation based on the physical simulation. This slide shows the effect of transformation on welding deformation of H-beam. The left one is regardless of transformation. The right one is considering the transformation. One transformation is considered the predicted maximum welding deformation of H-beam with 1 meter long is 3.48 millimeters. One transformation is ignored. The predicted maximum deformation of H-beam with 1 meter long is 5.06 millimeters. So from this picture, and we compare the actual the H-beam with 1 meter, we found if you consider the transformation, it's more close to the actual the welding deformation of H-beam. That means the transformation has some influence on welding deformation. For the high strength steel or the ultra high strength steel, we must consider the effect of transformation. Next, let's see the effect of welding sequence on welding deformation of H-beam. These are 4 welding sequence plans. Case 1 is just the 2 welds simultaneous welding, and weld 1 and 2 together simultaneously, and the other side is weld 3 and 4 simultaneous. The case 2 is first the weld 1 and weld 2 welding, but they are not simultaneous started. There is a 600 millimeters long distance. That is the weld 1 first started, and then for some time the distance is about the 600 millimeters and start the weld 2. The case 3 is weld 1, 2, 3, 4 completed in turn. The case 4 is just like case 2, but the welding direction in both sides is different. It's the reverse. Case 2 is the same direction. This is the welding deformation prediction result of 4 welding sequence plans for H-beam with 30 meters long. It can be seen from this slide that the total deformation of case 2 is the lowest, and followed by case 4, which is a little bigger than that of case 2. The difference between case 2 and case 4 is the welding direction. The welding direction of both sides of H-beam in case 2 is in the same way, while in case 4 it is the reverse direction. Since the total deformation of both processes is very small, does that mean both processes work well? This slide shows the wider deformation of case 2 and case 4. It is very clear that the H-beam in case 4 has a large distortion than that of case 2. So both sides of H-beam with the same welding direction, just as in case 2, is strongly recommended for our customer. This slide shows the effect of welding process on welding deformation of H-beam. One welding process is submerged arc welding. Its heat input is from 6 to nearly 20 kilojoules per centimeters. The other welding process is the mark welding. Its heat input is about 8 kilojoules per second. This is the result, the predicted welding deformation. From this slide, we can see that the maximum deformation of H-beam with 13 meters long is 8.393 millimeters for submerged arc welding. And the maximum deformation of H-beam with 13 meters long for mark welding is 3.107 millimeters. So it's very clear that the mark welding is strongly recommended for our customer. These are some very useful results for our customers to use to application our high strength steel or the ultra high strength steel. And these results of a numerical simulation are very useful to help our customers to improve their welding quality. However, please do remember, physical simulation is the base of the numerical simulation. Physical simulation is the key to build a better model for numerical simulation. Today, that's all we're sharing with you today. And thank you for your attention.
Well, I hope you all enjoyed the presentation. I did hear from some of our colleagues in China that they were not able to see the video, so I do apologize for that. It sounds like it was different locations depending on where they're accessing the internet. But we will be posting the full video online soon, and I did put a link in the chat area so you can download the presentation as a PDF. As I mentioned earlier, we won't be doing a live Q&A now. Dr. Chu was able to answer some questions in the chat, and so is our team. So I want to thank all of them for participating and answering questions. If you did miss any points, again, please watch that video and be sure to follow up with us. We'd be happy to either connect you with Dr. Chu or hopefully answer your questions directly. I also want to sincerely thank Dr. Chu for making this presentation and sharing it with us. It was great, very interesting. And I want to thank everybody that's listening for participating and joining us, and have a great happy holiday season. Thank you for joining us, and have a great day. Stay safe.